This is the video for part 2 of section 3.1, definition and examples of rings. We're going to start by looking at some additional examples of rings. So the set E of even integers with the usual addition and multiplication of integers is a commutative ring but has no identity. Now the verification of axioms R1 through R9 is straightforward. To show that E has no identity, we need to show that axiom R10 does not hold. So R10 is the existence of the multiplicative identity, which states that there exists an element 1 sub E in E such that for all A in E, A times 1 sub E equals A, and 1 sub E times A equals A. We can show that R10 does not hold using a proof by contradiction. So suppose there does exist an element 1 sub E in E satisfying the condition in the axiom. We need to then derive a contradiction. Now the hypothesis that A times 1 sub E equal A for all A and E in the axiom implies that 1 sub E must be equal to the integer 1. However, 1 is not an even integer, so 1 is not an E. So this is a contradiction, and therefore R10 does not hold, and so that proves that E does not have a multiplicative identity. For another example, let's look at the set O of odd integers with the usual addition and multiplication of integers, and this is not a ring. And to show this is not a ring, we need to show that at least one of the ring axioms fails to hold. Now all of the axioms hold except for R1, R4, and R5, so we can pick any of these three. So to show that R1, closure under addition, does not hold, well, this axiom states for all A, B, and O, A plus B is an O. And to show this does not hold, we just need to find a counterexample. So we can choose, for instance, A equal 3 and B equal 5. These are two odd integers. So then A and B belong to O, but their sum, A plus B, which is 8, does not belong to O. And therefore R1 does not hold. And hence O is not a ring with these operations. Now, even though the set of odd integers is not a ring with the usual addition and multiplication of integers, by introducing new operations we can obtain a ring. This shows that whether or not a set is a ring depends not only upon the set itself, but also the operations defined on the set. So for our example, we're going to let R equal O be the set of odd integers again, but with a new addition which will denote circle plus and a new multiplication circle dot defined as follows. So for each AB in R, the addition is defined by A circle plus B is A plus B minus 1, and the multiplication is defined by A circle dot B is A plus B minus A times B. This is where the operations plus, minus, and dot are the ordinary integer addition, subtraction, and multiplication. So then R is a commutative ring with identity with these operations. And we'll verify a few of the axioms to illustrate the procedure. So for R1, closure under addition, we need to show for all A, B, and R, A circle plus B is an R. So we'll suppose that A, B, and R are arbitrary odd integers, and we need to show that A circle plus B is an R. Now according to the definition of the addition, A circle plus B is A plus B minus 1, and since A and B are odd integers, then A plus B is even, and so A circle plus B, which is A plus B minus 1, will be odd, and hence A circle plus B is in R as required. Therefore R1 holds. Okay, we'll skip over R2 and R3, and let's look at R4. So this is the existence of an additive identity. So we need to show that there exists an element 0 sub R in R, such that for all A in R, A circle plus 0 sub R is equal to A. And to prove this, we need to show there exists an element 0 sub R in R that satisfies for all A in R, A circle plus 0 sub R is equal to A. So we'll set this up using this two-column approach. So on the left column we're going to find a 0 sub R, and then in the right column we're going to verify that 0 sub R satisfies our two conditions, the domain 0 sub R is in R, and our propositional function for all A in R, A circle plus 0 sub R is equal to A. Now to find 0 sub R, we note that the element 0 sub R must satisfy for all A in R the equation A circle plus 0 sub R is equal to A. And on the left side, this is a plus 0 sub r minus 1, and the right side is still a. And we can solve this equation now for 0 sub r. The a's will cancel, and this will give us 0 sub r is equal to 1. And so we'll choose 0 sub r equal to 1. So our additive identity element is going to be equal to the integer 1. Okay, well, going over to the right side, since 1 is an odd integer, then 0 sub r equal 1 belongs to r, so we've satisfied our domain condition. And then to verify the propositional function, we can suppose a and r is arbitrary. Then a circle plus 0 sub r is a circle plus 1, which is a plus 1 minus 1, which is equal to a. And this proves the propositional function. And so this proves the existential statement, and so therefore R4 holds. So we have an additive identity in our set, but it's not the typical additive identity that you might expect. And so in fact it turns out to be the integer 1. So next we have R5, existence of additive inverses. So this is for all a in R, there exists an n in R such that a circle plus n is equal to 0 sub r. So to prove this, we'll suppose a in R is an arbitrary odd integer, and we need to show there exists an n in R such that a circle plus n is equal to 0 sub r. So we'll set this up with our two columns again. So on the left column we're going to find an n, and on the right column we're going to verify that n satisfies the domain n belongs to R and the propositional function, which is a circle plus n equals 0 sub r. So now the element n must satisfy this equation, a circle plus n equals 0 sub r. And on the left side, this is a plus n minus 1. On the right side, 0 sub r is equal to 1. We just found that in proving axiom R4. And so solving this equation for n, we'll obtain n is equal to minus a plus 2. So this is going to be our additive inverse. And again, this is a little different than we would expect for an additive inverse. So on the right side, we can verify our two conditions, and we can say that since n is an odd, this is there's a typo there. It should say since a is an odd integer, then minus a is odd. So n equal minus a plus 2 will also be odd, so that belongs to R. The propositional function holds since a circle plus n is equal to a circle plus minus a plus 2, which is equal to a plus the quantity minus a plus 2 minus 1, and this works out to be 1, which is equal to our additive identity, 0 sub r. And this proves the existential statement, and therefore R5 holds. Now, since our addition in this example is not the standard addition of integers, the additive identity is different from the additive identity for the standard addition. And also note that in verifying R5, when determining the additive inverse of an element, we need to use the additive identity found in R4. So R5 involves the additive identity 0 sub r, and so we need to use the specific additive identity that we prove works in R4. And we do not want to use the identity for the standard addition. So next we'll look at R6, closure under multiplication. So this is for all a, b, and r. A circle dot b is in R. So we'll suppose that a, b, and r are arbitrary odd integers, and we need to show that a circle dot b is in R. And according to the definition of the multiplication, a circle dot b is a plus b minus a times b. And since a and b are odd integers, then a plus b is even, and a times b is odd. It follows that a circle dot b, which is a plus b minus a times b, will be an even minus an odd, which is going to be odd. And hence a circle dot b is in R as required. And therefore R6 holds. We'll do one more axiom. We'll do the first distributive law in R8. Okay, so R8 contains two distributive laws, so we'll just do the first one. So we'll suppose that A, B, C in R are arbitrary, and we need to prove this equality. A circle dot B circle plus C is equal to A circle dot B plus a circle dot C. And really we should have parentheses on the right side of that equation as well, as shown in the symbolic form. So now the left side is a circle dot times the quantity B circle plus C, and this is going to be a circle dot B plus C minus 1. And this is going to be a plus the quantity B plus C minus 1 minus a times the quantity B plus C minus 1. And simplifying this, this works out to 2a plus b plus c minus ab minus ac minus 1. The right side is as shown, so it's the quantity a circle dot b plus the quantity a circle dot c. And this will be the quantity a plus b minus ab circle plus the quantity a plus c minus ac. And this is, using the definition of our addition, a plus b minus ab plus a plus c minus ac minus 1. Now simplifying this, this is going to work out to 2a plus b plus c minus ab minus ac minus 1. And we can see that the two sides are equal, so the distributive law holds as required. And therefore the first distributive law in R8 holds. Okay, next we want to talk about some special types of rings, some additional special types of rings, and the first is integral domains. Now we noted earlier that the set of integers z had one additional property that we haven't talked about in this section, the zero factor property. So a ring with this property is called an integral domain. So here's our formal definition. An integral domain is a commutative ring R with identity 1 sub r not equal to 0 sub r that satisfies the additional axiom R11 is the zero factor property for all a, b, and r. If a times b is 0 sub r, then a equals 0 sub r or b equals 0 sub r. Now the condition 1 sub r not equal to 0 sub r is included in our definition to exclude the single element ring consisting of just the additive identity 0 sub r from the class of integral domains. And for this ring, okay, so this was the example that was done earlier in the section, the zero factor property will hold trivially since the conclusion will always be true. So if the ring only contains the zero element, then obviously the conclusion in the zero factor property will be true. So we just want to exclude this specific ring from the class of integral domains, and so we include that condition that the identity the multiplicative identity 1 sub r is not equal to the additive identity 0 sub r. For an example, well, for all integers p greater than 1, if p is prime, then z sub p is an integral domain. And for all integers n greater than 1, if n is not prime, then z sub n is not an integral domain. And the proof of 1 is contained in theorem 2.8. So in theorem 2.8 we showed that in the case that p is prime, z sub p satisfies the zero factor property, so therefore z sub p will be an integral domain. To prove 2, we'll go ahead and suppose that n is not prime, and we need to show that z sub n is not an integral domain. And to show this, we need to show that z sub n does not satisfy the zero factor property. Since n is not prime, then it has positive divisors a and b such that n is equal to a times b, and both a and b are strictly greater than 1 and less than n. And so if we consider the elements the class of a, class of b in z sub n, since both a and b are strictly between 1 and n, then the class of a is not equal to 0, and the class of b is also not equal to 0. So these are two non-zero elements in z sub n. However, their product, class of a circle dot class of b, will be equal to the class of ab, which is equal to the class of n, which is equal to the class of 0. And this shows that z sub n does not satisfy the zero factor property, and so that means it's not an integral domain. So we have one more special type of ring to consider, and that's a field. And so the set of rational numbers q is also an integral domain. However, q has one additional property that z does not have. Every non-zero element in q has a multiplicative inverse. And we give one more special name to rings with this property. And so a field is a commutative ring R with identity, multiplicative identity 1 sub r not equal to 0 sub r that satisfies the additional axiom, and we'll call this R12, and this is existence of multiplicative inverses. So for each a in R, a not equal to 0 sub r, so a is a non-zero element, there exists an element x in R such that a times x is equal to 1 sub r. So x will be a multiplicative inverse for the element a. And again, we include this condition that 1 sub r is not equal to 0 sub r to exclude the single element ring consisting of just the 0 sub r from the class of fields. And for this ring, axiom R12 will vacuously hold since there are no non-zero elements. So if there's no non-zero elements, then every non-zero element has a multiplicative inverse. And again, we just don't want to include this particular ring or call this particular ring a field. For some examples, well, the set R of real numbers with the usual addition and multiplication of real numbers is a field. And let's let C be the set of complex numbers, which is defined by the set of quantities a plus bi, where a and b are real numbers, where I squared is equal to -1. So I is the square root of -1. And our addition and multiplication are defined as follows. So for all a plus bi, c plus di in C, our addition is defined by adding the real parts, the a plus c, and the imaginary parts, the b plus d, separately. And for multiplication, we multiply two complex numbers together, basically using FOIL. So a plus bi times c plus di works out to be ac minus bd plus ad plus bc quantity times I. Then C is a field. Okay, you can verify all of the ring axioms hold together with the commutative law of multiplication, the existence of a multiplicative identity, and the existence of multiplicative inverses. Next, we want to look at some ways to construct new rings from old. And we'll start with an example. So let's let T be the Cartesian product Z3 cross Z4. So this is the set of ordered pairs AB, where A comes from Z3 and B comes from Z4. And we can define addition and multiplication component-wise as follows. So for all ordered pairs AB and CD in Z3 cross Z4, AB plus A prime B prime is equal to A plus A prime, B plus B prime. Okay, and I can see that I really intended to have AB and A prime B prime instead of CD. Okay, and then multiplication is also defined component-wise, so AB times A prime B prime will be A prime, B prime. Then you can show that T is a ring. Okay, and this example can be generalized to arbitrary rings. So this is contained in theorem 3.1. So let's let R and S be rings, and we can define addition and multiplication on the Cartesian product R cross S, which is the set of ordered pairs RS, where R comes from capital R, should be a capital R, another typo there, and S comes from S, component-wise as follows. So for all RS, R prime, S prime in R times S, or R cross S, addition is defined component-wise. So the ordered pair RS plus the ordered pair R prime S prime is the ordered pair R plus R prime S plus S prime. And multiplication is also defined component-wise. So RS times R prime S prime is equal to R prime S prime. Then R cross S is a ring. Okay, and the proof of this is omitted, but it's fairly straightforward, just verifying the axioms of a ring. And furthermore, if R and S are both commutative, then so is R cross S, and if both R and S have a multiplicative identity, then so does R cross S. Okay, next we want to talk about subrings. So suppose R is a ring and S is a non-empty subset of R. If S is itself a ring under the addition and multiplication of R, then S is called a subring of R. Now, according to the definition, in order to show that a subset S of a ring R is a subring, we would need to verify that S satisfies the 8 ring axioms. However, it turns out that a subset will inherit many of the properties of the ring. For instance, to show that S satisfies axiom R2, we would need to show, so R2 is the associative law of addition, so for all A, B, C in S, A plus the quantity B plus C is equal to the quantity A plus B plus C. And to prove this, we would start by supposing A, B, and C are arbitrary elements of S, and we need to prove the equality. Now, since S is a subset of R, then A, B, and C will all belong to R. And since R is a ring, then we know that R2 holds in R, and therefore this equality holds as required. So we can similarly show that axioms R3, R7, and R8 will also hold in S. So we don't actually have to do any work in order to conclude that these 4 axioms, R2, R3, R7, and R8, hold in a subset of a ring. So it remains only to verify the remaining 8 of the 8 axioms, R1, R4, R5, and R6. And the following theorem shows that we do not actually have to verify axioms R4 and R5, but only 2 weaker statements. So this is theorem 3.2, and this says suppose R is a ring and S is a subset of R. Then S is a subring if and only if it satisfies the following 4 properties. So 1 is closure under addition for all A, B, and S. A plus B is an S. So we're dealing with properties of the subset S now. And 2 is closure under multiplication for all A, B, and S. A times B is an S. 3 is containment of the additive identity, which just says that 0 sub R is in S. And 4 is containment of additive inverses. For each A and S, the additive inverse minus A belongs to S. And to prove this, well, the forward direction follows immediately from the fact that a subring is a ring and hence satisfies axioms R1 through R8. So for the forward direction, it would say that if S is a subring, then it satisfies properties 1 through 4. Well, if S is a subring, then it satisfies axioms R1 through R8, so it will certainly satisfy these properties 1 through 4. To prove the backward direction, let's suppose that S satisfies properties 1, 2, 3, and 4, and we need to show that S is a subring. To show this, we need to show that S satisfies axioms R1 through R8. And now, as discussed above, S will inherit axioms R2, R3, R7, and R8. So we only need to show that S satisfies axioms R1, R4, R5, and R6. Now, property 1 is identical to R1, that's closure under addition. And property 2 will be identical to axiom R6, that's closure under multiplication. So if we're supposing that S satisfies properties 1, 2, 3, and 4, then that tells us that R1 and R6 are also satisfied. So it then remains only to show S satisfies R4 and R5. Now, to prove S satisfies R4, we need to show there exists a 0 sub R in S such that for all A and S, A plus 0 sub R is equal to A. Now, by property 3, 0 sub R belongs to S. And since 0 sub R is the additive identity for the entire ring R, then we know that A plus 0 sub R is equal to A for all A and R. It follows then that A plus 0 sub R will be equal to A for all A and S. So if we know that the additive identity has this property for all elements in R, it's certainly going to follow that it has the property for all elements in S, since elements of S belong to R. Therefore, S satisfies axiom R4. To prove S satisfies axiom R5, we need to show for all A and S there exists a minus A in S such that A plus minus A is 0 sub R. So we'll suppose that A is an arbitrary element in S, and by property 4 now, the additive inverse minus A does belong to S. Since minus A is the additive inverse of A in R, then A plus minus A is equal to 0 sub R, and therefore S satisfies axiom R5. And so thus S satisfies all the ring axioms, so is a subring. And this completes the proof of the backward direction, and this finishes the proof of the theorem. Now, note that property 3 in the theorem only says that the subset S contains the additive identity 0 sub r of the ring R. To verify this property, we only need to show that S contains 0 sub r, and not that 0 sub r has the property of an additive identity, that for all A and S, A plus 0 sub r is equal to A. So this is property 3 is a weaker condition than axiom R4. And so this property of an additive identity follows automatically from the fact that 0 sub r is an additive identity for the entire ring R. Similarly, property 4 in the theorem only says that for any element A in S, the subset S contains its additive inverse. To verify this property, we start with an arbitrary element A in S. We then need to show that minus A belongs to S. We do not need to show that minus A has the property of an additive inverse, that A plus minus A is equal to 0 sub r. That follows automatically from the fact that minus A is an additive inverse for A in the ring R. So again, property 4 is a weaker property or a weaker condition than axiom R5, and so it makes it easier to verify.